Good afternoon, everybody, and welcome to the lecture number 14 on the body plots. So, in our last lecture, we have discussed about the initial slope line, that what should be the slope of the initial line of the magnitude plot. It depends upon the number of poles and number of zeros at the origin. We have understood through one table, and then we have also seen that once the initial slope of the initial slope line is determined, then where it crosses the 0 dB axis, that we have also seen that it crosses at omega is equal to certain values of k. Then we need to prepare the table, and the table consists of the terms, then corner frequencies, then slope contribution, and final slope. So let me revise this. Each and every term in the transfer function is contributing the corner frequencies, except a pole at origin or a zero at origin and steady state gain. These three terms will not contribute in the corner frequencies. Then the slope contributions. Steady state gain k will not contribute any slope, but a pole at origin will contribute a slope of minus 20 dB, one pole. If there is a two pole, then the slope would be minus 40 dB per decade. 1 0 slope would be plus 20 dB. 2 zeros, the slope would be plus 40 dB per decade. Okay. Note that these corner frequencies should be in the ascending order. Okay. So the lowest corner frequency at the top, and the highest corner frequency or the largest corner frequency is on the bottom. So, for example, let us see one example and then we'll prepare this table. Okay. So, example is something like this. Let's say I have converted the transfer function into its time constant form already. Okay, and let's say it is this. Okay, you need to convert this into a time constant form. Okay. All right. So I'm assuming that you can say this is, you need to convert into, so you, let's say s square by, let's say 10 by 10 plus 1. Okay, something like this. So this is in the time constant form already. So this term is in the time constant form, tau s plus 1. This is also tau s plus 1, but it is a square term. This is a second order term, standard second order term. Okay. So the steady state gain k is 20. So it means that this k is 20. This is the steady state gain k. Now, what are the terms? Terms are k, 3s plus 1 on the numerator, s square on the denominator, 2s plus 1 whole square on the denominator, and there is a second order term on the denominator. So I need to find the corner frequencies first. So k is equal to 20. Okay, so I'm writing k is equal to 10. So then now the corner frequency for this term, there is no corner frequency. For 3s plus 1, it is tau s plus 1. So the corner frequency for the first order term is 1 by tau. So tau is 3. So 1 by tau. So corner frequency is 1 by tau is 1 by 3. So here for this term the corner frequency is 1 by 3. For this term there is no corner frequency. For this, the corner frequency, actually it is a second order term. but consists from first order term. So it would be considered as first order term. So the corner frequency would be tau s plus 1. So 1 by tau. Corner frequency is 1 by 2. Okay. Even though it would be a second order term, it's fine. Okay. Corner frequency is 1 by tau. So if there is a real pole, the corner frequency is 1 by tau. Okay. If there is a complex conjugate pole, then it is a second order term. So here the corner frequency is omega n. Omega n is, what is omega n? Omega n is, you have taken 10 out. Okay. So this term is actually, this term was something like this, s square plus 9s plus 10. Okay. You have taken 10 common. So s square by 10 plus 9 by 10 plus 1. Okay. It was something like this. So because you need to compare with this s square plus 2 xi omega ns plus omega n square. So omega n square is 10. So omega n square is 10. So omega n is equal to root of 10. Okay. Root of 10 is something like 3 point something, 3.36, let's say. Okay. So k, or let's say if it is 100, then omega n square is 100. So it is exactly 10. Okay. So corner frequency for this term is 10. So now these are the corner frequencies. 1 by 3, 1 by 2, 1 by 3, 1 by 2 and 10. So I need to arrange in the ascending order. So corner frequency would be 1 by 3, then 1 by 2, then 10. So this is the lowest corner frequency, this is the highest corner frequencies. So this is how I have rearranged the corner frequency. So now I should know that 1 by 3 is the corner frequency from which term? From 3s plus 1 term. 1 by 2 is the corner frequency from which term? That is 1 by 2s plus 1 whole square. 10 is the corner frequency from the which term? It is from the second order term in the denominator. Okay. See, this second order term can be on the numerator also. Okay. But the slope contribution would be different. Alright. We have also seen that slope contribution from the numerator or from the zeros would be positive. From zeros, slope is positive. From the poles, from the denominator term, the slope is always negative. From first order term, slope would be plus minus 20. For second order term, slope minus plus minus 20. Okay. For second order term, slope would be plus minus 40. Okay. All right. Now, so once we find the corner frequencies, we need to rearrange this, all this. So what should I do? I am writing this transfer function here. 20 3s plus 1 s square 2s plus 1 whole square s square by 100 plus 9s by 100 plus 1. Okay. So I am taking this out. So the term k means 20 here. Okay. Term is 20. Corner frequency, there is no corner frequency. Slope contribution, there is no slope contribution. Okay. Final slope, no final slope. So I have taken this into consideration, terms 20. Then I need to write a pole at origin or a zero at origin. So here it is, there is a pole at origin. So 1 by s square. This term, okay. 1 by s square. What is corner frequency for this term? There is no corner frequency. Okay. What is the slope contribution? See, there are two poles in the denominator for this term, 1 by s square. So contribution from pole is always negative, and from one pole it is minus 20. For two pole it is minus 40 dB per decade. And that's why the initial, okay, and what is the initial slope line? Initial slope line is type 2 system. Type 2 system is slope contribution would be minus 2 into minus 2 into 20 dB per decade. So minus 40 dB per decade. So the slope contribution is minus 40. So final, earlier there was no slope, now minus 40. So final slope is minus 40 dB per decade. Alright. So this term is over. Now so all the terms which doesn't have corner frequency, that we have written 20 gain and the 1 by s square. Okay. Now we need to write the terms from according to the corner frequencies. So the lowest corner frequency is 1 by 3. 1 by 3 is contributing from which term? 3s plus 1. This is the term. Corner frequency is 1 by 3. Okay. I'm talking about this. And the slope, since 1 by 3 is the corner frequency contributing from a term, a first order term on the numerator side. So the slope contribution would be plus 20 dB per decade. So earlier the slope was minus 40. Now the slope is changing to minus 40 and adding plus 20. So minus 40 plus 20 is equal to minus 20 dB per decade. The final slope is minus 20 dB per decade. So this term is over. Then 1 by 2. 1 by 2 is contributing from which term? This term, a second order term. That is 2s plus 1 whole square. But how many poles of this term? 2 poles. So slope. What is the corner frequency? First of all, from this term, 1 by 2. And then what is the slope contribution? Since there are 2 poles is minus 40 dB per decade. Okay. If it is minus 40 dB per decade, earlier slope was minus 20. Now the slope is minus 20. So minus 20 minus 40 dB per decade. So it would be minus 60 dB per decade. Okay. All right. Again, yeah. So please ignore this term, this space. Okay. All right. Then the term is the next corner frequency is 10. 10 is contributing from which term? From this term, second order term. Which term? Which is this, s square plus 9s plus 100. This is the term. What is corner frequency is 10. It is which term? It is the second order term on the denominator. So slope contribution would be minus 40 dB per decade. Okay. So earlier slope was minus 60. So minus 60 minus 40. So it is minus 100 dB per decade. So this is how the table is complete. So now the magnitude plot will start from a slope line whose slope is minus 40 dB per decade. It will continue. It will cross this line, minus 40 dB per decade line will cross the 0 dB axis at omega is equal to, since it is 1 by square, so omega is equal to root of a. Okay. So it will cross there. At frequency 1 by 3, because the slope is minus 40 dB per decade, then at corner frequency 1 by 3, as soon as that line comes, the initial slope line comes at 1 by 3, omega is equal to 1 by 3, its slope will change to minus 20 dB per decade. So then from minus 20 dB per decade, it will continue till 1 by 2. Then the slope from 1 by 2, slope will change to minus 60 dB per decade. From minus 60 dB per decade, it will continue till omega is equal to 10. Then from 10, the slope would be minus 100 dB per decade. This is how at every corner frequency, 1 by 3, 1 by 2 or 10, the slope of the magnitude plot is changing. So it is, so let's say it is CF1, CF2 and CF3. Okay. All right. So let's say, for example, let's say this is CF1, this is CF2, and let's say this is corner frequency 3. The initial slope line was minus 40 dB per decade, and let's say minus 40 dB per decade is initial slope line is minus 40 dB per decade, and it was crossing, this line was crossing at omega is equal to root of k, and k was 20. Okay, so omega is equal to root 20. Okay, so it would be something like 4.2. So let's say 4.2 is here. Okay, 4.2 is here. Okay, omega is equal to 4. So I need to draw a line of minus 40 dB per decade which is passing through 4.2. So let's say this is the line. Okay, This is the line whose slope is minus 40 dB per decade. So now this is the initial slope line, which is crossing at omega is equal to root of k. Then at corner frequency 1, the slope is minus 60 dB per decade. Okay, so at corner frequency 1, at this point of time, the slope is minus 60 dB per decade. So this is minus 60 dB per decade. It will continue till corner frequency 2. Let's say this is corner frequency 2, or you can say like this. Sorry. Let's say this is CF2. Okay, and let's say, so now this is the line. So this is minus 40 and this is minus 60 dB per decade. Now it will continue to minus 60 minus 100 at corner frequency. We forget about, actually it was not minus 60, but it was earlier the slope was minus 40, then actually plus 20 it was there. Okay. Let me do it again. If you remember the table, then earlier the slope was minus 40, then minus 40 plus 20, then minus 40 plus 20 plus minus 20, then minus 40 minus 20, then minus 40 minus 20 minus 40. Okay, so the slope is minus 40 minus 20, then minus 40 minus 60 and minus 100. This was the case. Okay, if you look into the slope, final slope contribution, it was something like this. Now let's say this is CF1, this is CF2, this is CF3, let's say. So this is 1 by 3, 1 by 2, and this is 10 corner frequency. Okay, and this is omega is equal to 4.2. 4.2 is, let's say, here 4.2. Okay, now I need to draw a line which is having initial slope line is minus 40 dB per decade, which is passing through this line. Okay, so I'm drawing a line, let's say this. Okay, so the slope of this line is minus 40 dB per decade. So the initial slope line coming, and it will not change the slope till corner frequency 1. So corner frequency 1 is this. So I can say like this. So this is the magnitude plot. Okay, this is all magnitude plot. Now at corner frequency 1, the slope is changing to minus 20. So this was minus 40. So now it is changing to minus 20. Okay, this is continue. This is over. Then minus 20 slope. So this is minus 20 dB per decade. It will continue till corner frequency 2. So till 2 means this. So this is the magnitude plot. Then comes minus 40 dB. So it is a parallel to this again. It will continue. So this is till corner frequency 10. So it is this. So this is minus 40 dB per decade. Okay. Then the slope is minus 40. Then the slope is actually 60 dB. Again, we are doing some mistake. I don't know. Minus 40. Then there was a 0. This. Oh, this was 60 directly. Okay. Minus 20 plus 40. This is 60 dB. Okay. Yeah. Then comes 100 dB. Okay. So let's say this is 100 dB. Okay. It will continue till last. So this is the magnitude. So this is the magnitude. You can see that the initial slope line is having the slope of minus 40. Then this is the from the 0 contribution from 1 by 3. it is minus 40 plus 20, so minus 20, then minus 20 minus 40, so minus 60, minus 60 minus 40, so minus 100 dB. So this is having minus 100 dB per meter square. This is how we can draw the magnitude plot. All right. Now the problem is, so if it is type 1 system or type 2 system, then the initial slope line is going to intersect the 0 dB line. So we can find that the omega from where the initial slope line will pass. But what happens if there is no pole at origin or no zero at origin? It means that the line, the magnitude plot, initial slope line is parallel to this. It will never cross. So it means that the line is parallel to this. It will never cross this 0 dB line. Okay, this is 0 dB line because there is no slope. So line is parallel. So so this is also a parallel line. This is also a parallel line. This is also a parallel line. Which line is correct? So for that, so for type 0 system, initial slope line is parallel, right, to 0 dB axis. Means type 0 system means neither pole or nor 0 at origin. So there is no term on the numerator, or there is no term on the there is no s term on the numerator, or there is no single s term on the denominator. In that case, the initial slope line is parallel to the 0 dB line. So it can be parallel from this point also. It can be parallel from this point also. So what should be this? If I know this distance, then I can draw that line. Okay. So what about that distance? So that distance is 20 log of k. We know the value of k. If you do the 20 log of k, then this line, this distance is 20 log k. It will continue till the first corner frequency. Then it will change. Again, next corner frequency, it will change the slope. Okay. This is corner frequency 2 and so on. It will, so at every corner frequency, the slope of the magnitude plot is changing. It can be increased if it is contributing from 0. It can be decreased if it is contributing from poles. Let us finish this lecture here only. In the next class, we are going to start with the phase plot. Thank you.